please.
Miguel, thank you very much. So it's a great pleasure for me to be here today in my hometown. So we're going to start off this course now with just a broad introduction to NMR Physics. So I work in an imaging research centre based in St James's Hospital and the University of Dublin. So this is just an overview of the talk, so I'll just give a very, very brief introduction to the world of MRI. I'll give some of the basic underpinning physics of the nuclear magnetic resonance technique. We'll very quickly look at the basic system components. You'll be getting more detail on specifically on RF coils in the second lecture this morning. And then finally I'll just mention some imaging protocols and basically how we acquire an image. So just to begin then with introduction to MRI. This is a picture of a very modern clinical whole body scanner. It's a very large and expensive piece of equipment, one of the most expensive you'll find in a hospital, so you just about 1.5 to 2 million euros. Most of what you see is just a very large magnet, generates a very large magnetic field directed along the bore of the magnet like this. This is a 3 Tesla scanner, Tesla being the unit of magnetic field strength, so it's a very, very strong magnet. This would be the very first whole body scanner built back in 1979. Had a vertical magnetic field generated by the black coils you can see here. Much smaller magnetic field strength, so things have obviously progressed quite a bit since then. And this will be one of the typical first images obtained, so an actual slice through the abdomen. You can see the liver here and the spinal cord here and the left and right arms over here. And just to compare it with an image we'd get on a modern scanner, you can see there's been quite a large improvement, as you'd expect. Just very briefly to give a timeline of MRI itself, a lot of the very basic physics was discovered back in the 1920s and 30s when a lot of the Pauli suggested that nuclear particles would have this spin angular momentum property, and then some of the early experiments to actually measure the strength of this and to be able to realise that these nuclei would absorb energy in a resonant fashion. And a lot of this activity was rewarded with Nobel Prizes for the physics developments in the 40s and 50s. And in the decades since that time, this nuclear magnetic resonance technique was used mainly in spectroscopy systems. So you had a lot of NMR spectrometers in chemistry departments all over the world. And this was recognised by Nobel Prizes in chemistry in the 1900s and around 2001. Now, it wasn't until the early 70s that the idea to expand NMR into imaging came about. Lotterer and Mansfield were two people who were primarily involved in the early days with this invention, with the first scanners being built in the late 70s and first commercially available clinical scanners being available in the early 1980s. And again, this was recognised in 2003 by a Nobel Prize for these guys in medicine. So MRI has a number of advantages compared to some other imaging technologies. It's got very good and flexible image contrast, so you can see identical slices of the brain here where different brain structures appear differently in the images depending on how we acquire the images, depending on exactly what we're looking for. Obviously, it's non-invasive, there's no ionizing radiation involved. We can scan the subject in any arbitrary plane. But there are a number of challenges where people are trying to develop the technique so we can image much faster compared to CT, for example, X-ray CT. It's a bit slower to acquire high-resolution images over a large part of the body. And we're always trying to investigate newer methods for introducing contrast into images and also new contrast agents, which are constantly being developed, and there's an enormous potential there as well, even for MRI. So as I mentioned, radiographically, these would be the standard 3 orientations that we can acquire images in, but we can orientate slices in any plane that we wish. Okay, so just to move on to talk about the underpinning physics of nuclear magnetic resonance. The technique is commonly called MRI, but it's really more accurately termed nuclear magnetic resonance. The nuclear term was dropped, I suppose, when they were trying to popularise the technique back in the 70s and 80s. And it's based around this fundamental property of many particles called spin. It's related to angular momentum. And it's a fundamental property of some elementary particles. So, for example, the electron has a spin. It's got a value of spin of 1/2, and this gives rise to the technique of electron spin resonance, which, again, people are trying to develop this into an imaging technology as well. And it turns out some nuclei also have a property of spin. It can have a value of 1/2, 1, 3/2, etc. And examples are hydrogen, carbon, fluorine, sodium, etc. So many elements within the periodic table have this property of nuclear magnetic spin. So, as the term suggests, we're actually focusing on the nucleus of atoms, and it turns out that there's a lot of protons in the nucleus with positive electric charge. So a positive electric charge which is spinning gives rise to a magnetic moment. So it turns out that we can consider the nuclei to act like small magnetic dipoles, North Pole, South Pole. And this has formed the basis of the physics of the MRI technique itself. Now, in the body, the most prevalent atom is hydrogen. So the nucleus is just one proton. It's positively charged. It has a spin of a half. And so we can consider the hydrogen nuclei in the body to act like tiny magnets. Now, in MRI, we're mainly looking at hydrogen in water molecules. There happens to be a lot of that in the body, which is quite fortuitous for imaging. The water molecules in the body exist in different types of environments, intracellular, extracellular, intravascular. All of these contribute to signals, and we can use different acquisition techniques to try and separate out signal from each one, depending on our application as well. We also have hydrogen nuclei, of course, in lots of other molecules in the body as well. But predominantly, it's mainly from water. Distribution in the body that we're getting our signal. So, as I mentioned, there's quite a lot of water, so we can achieve a very large signal, and so we can produce very nice images. Now, in the normal state of tissue, if we look at the magnetic dipole moments on all, individual hydrogen nuclei in the body, normal state, if we just have some water in a bottle here, the molecules are tumbling around very rapidly, of course, and their magnetic dipole directions are pointing randomly in various different directions. Now, if we take this and apply a very large magnetic field, so we take the water or the patient and put it into an MRI scanner, just putting it into the magnetic field, so we have a very large magnetic field indicated by the symbol B here, and what we do is we force an alignment of the magnetic moments on the individual hydrogen nuclei with the direction of this externally applied magnetic field. Now, you'll notice here that some of them are applied with the North Pole, South Pole aligning with the direction of the magnetic field, and some are aligned anti-parallel to it, and this is quite significant. So this is the situation when the magnetic field is zero, they're all randomly aligned. Once we apply a magnetic field, we call it B0, so a static, unchanging magnetic field. What we're doing is we're actually separating out the nuclei, some which have a spin which is parallel to the externally applied magnetic field, and others which have an anti-parallel alignment. Now, this is what we would call an energy level diagram. So we're kind of plotting energy in the vertical direction here. And it turns out that all of these spins here, we call them spins, have the exact same energy. So once they're aligning parallel to the magnetic field, we consider them to have a very definite energy level indicated here. And the ones which are anti-parallel have a higher but also equal energy level among themselves. And we know that there's a very definite energy gap between these two energy levels. And it is a quantum effect in that spins are either parallel or they're anti-parallel, and there's nothing in between. So we use this term polarization to explain what happened. By placing the sample into a magnetic field, we've effectively polarized the sample. And this would be the situation that we would get at room temperature. So it's called the splitting of the energy levels, which was first discovered by Zeeman. It turns out we can define the relative population of the two different energy levels for a given magnetic field and temperature range. So the ratio of the anti-parallel, the numbers which are aligned anti-parallel to parallel, is given by this e to the power minus the energy gap divided by kT, k being a constant, Boltzmann's constant. And it's interesting to note from this equation that we have this dependence on temperature here. So if we put the temperature to zero, it turns out that all of the spins would be in the lower energy state. But once we go to room temperature or to body temperature, it turns out that the population difference between the two levels is very, very small. Okay. Now the second thing to note is this energy gap here. We can derive an expression for the actual separation of the energy levels between the two spin populations. The energy gap is directly equal to the magnetic field that we've applied, plus some other constants, gamma jar magnetic ratio and Planck's constant, just constant for a particular nuclei. And so it turns out that if we have a static magnetic field of 1 Tesla, the excess population is very, very small, 3.3 parts per million. Is the difference in population between the two levels. If we increase the magnetic field strength, we're increasing the population excess, 3 Tesla over 10. And this is the driver behind developing systems with larger and larger and larger magnetic field strengths, because we're simply increasing the excess population between these two different energy levels. So the inherent sensitivity of an NMR experiment is actually quite small if you compare it to some other imaging modalities. So only 5 parts per million actually contribute to our signal. It's a net effect which is contributing to our signal. Nevertheless, because we have such a large number of protons in the body, even a small few parts per million is still enough to actually give us a signal. There are some newer techniques which are trying to hyperpolarize the sample at room temperature, so rather than just have the ordinary thermal polarization of the two levels, to try and actually stimulate some extra spins to the upper energy level before we even do any imaging. And so that's making the imaging of things like carbon and xenon much more possible, and they have very exciting applications as well. So if we just consider now the excess spins that we have in the lower energy level, that's all we need to think about. They're all pointing parallel to the externally applied magnetic field. So if you average across all of these individual trillions of effectively magnetic fields from each hydrogen nuclei, they will sum together to give what we call the net magnetization vector, M subscript 0. So it's pointing in the direction of B0. And it turns out this is what we're trying to measure in a patient. So different tissues perhaps will have different values of M depending on density, depending on many other properties as well. And we're going to try and measure this, and we do this by manipulating the direction of this vector by applying radio waves, as it turns out, so oscillating magnetic field at a very specific frequency. So just to give us a coordinate system, in the picture I showed you earlier on, the patient is lying horizontal down the bore of this cylindrically shaped magnet. We're just going to orientate it vertically now. So the person is lying along the bore of the magnet. This is the direction of B0. Once we put them into this large magnetic field, we're effectively generating this vector M, the net magnetization, along the direction of B0. And so we call this the Z direction, or the longitudinal direction, as opposed to the XY plane, which will be in the transverse plane. And what we're going to try and do is rotate this vector M into the XY plane. It turns out that when I said they're actually parallel, they're not quite parallel, they're at a slight angle. And so what we tend to have is, if this is the direction, the Z direction here of our externally applied magnetic field, this will be the direction of the M0 vector, and it is actually at a slight angle, and it's precessing around the direction of the main magnetic field. And it turns out that we can derive an expression which gives us the frequency of precession. Again, the frequency at which they're rotating around is directly equal to the applied magnetic field strength, again multiplied by this constant, which is a particular number for particular nuclei. And this is called the Larmor equation. So the spins are precessing at the Larmor frequency. Okay, so in an NMR experiment, what we're trying to do is we're trying to excite the spin system. So we go back to our energy level diagram. We have a number of spins which have their alignment parallel to our external magnetic field in a lower energy level, and a number which have their alignment anti-parallel, so in the higher energy level. And what we're going to try to do is take one particular spin here and excite it to the upper energy level, which corresponds to taking its spin direction and flipping it anti-parallel. Okay, so to do this, we need to give energy into the system. Okay, so we want to take this guy here and promote him to the upper energy level. We know that there's a particular energy gap. So once we put the sample into a particular magnetic field strength, we quantify exactly what the energy gap is. And so we just give some energy in. It turns out the energy we supply to the system must be very precise, and this is what gives rise to our resonance phenomenon. So if it's not enough energy, nothing will happen. If it's too much, nothing will happen. So it must be very, very exact. So we know the energy gap. We had this expression earlier on. It turns out the energy we're putting in will be electromagnetic photons. And so we know the energy of a photon is given by h bar omega. And so if the energy gap has to be equal to the energy that we put in, these two quantities must be the same. And so we just cancel out, and it turns out the frequency of the photons that we put in must be again equal to its gamma B0, which is the same frequency as the Larmor precessional frequency that the spins are precessing at around the direction of our external B0 field. It turns out that when we're working with a 3 Tesla magnet, the frequencies of the photons that we need to put in happen to be around the megahertz range. Okay, so it's just gamma B0. So we call this the radio frequency range. So your local radio station is up in the hundreds of megahertz, 105 FM. So this will be the megahertz range. At 7 Tesla magnetic field strengths, we're at 300 megahertz. The next jump in field strength is typically 9.4 Tesla, because that corresponds to 400 megahertz. 11.7 Tesla will be 500 megahertz, etc. And you can compare this to light photons, which just have that much higher energy, that much higher frequency, and again X-ray photons, which have so much energy that they would actually potentially create damage passing through tissue. Okay, so the spin population absorbs this energy that we have applied in. and it's applied in an electromagnetic field. We're actually considering the magnetic component of this electromagnetic field, so we're actually calling it the B1 field. Okay, so this is opposed to our B0 static 3 Tesla field, if you like. And what we're doing in MRI is we're sending in a very short pulse of this radio frequency energy. So we just turn it on for a very short time. It's usually of the order of microseconds, or hundreds of microseconds. And immediately after the sample has absorbed the energy, we can say that the sample is now excited. So provided the energy is at the exact frequency that's needed, the sample will absorb it. It absorbs it by affecting these transitions between the energy levels, and so the sample is now excited. And as you might expect, it won't stay excited forever. It will eventually relax back to its equilibrium situation. So what we have is this vector M0, which was initially pointed along the direction of B0. This was the average of all the trillions of excess hydrogen nuclei in the lower energy level. What happens is when we apply these radio waves, we're exciting transitions from the lower energy level to the upper energy level, so flipping spins over. And the net effect of this is that we cause this vector to actually precess. I don't know if I can get this video to run, this one here. Is that possible? No? So what we have is the vector M is initially pointing along the direction of the external magnetic field, and it gradually spirals down as we're applying our RF energy. And when we turn off the energy, in this situation, we've just supplied enough energy to affect a rotation of 90 degrees, so from the Z direction down into the XY plane. Okay. Now, it does actually spiral down because it's actually precessing around the direction of both the B0 field and the B1 field. The B1 field being this electromagnetic photons that we sent in. Now, sometimes to avoid just the effect of looking at a spiraling vector coming in here, we can imagine we're in a frame of reference where we're rotating at the Larmor frequency as well. So it effectively looks like this white vector here is M0. It was initially along Z, and it's simply rotated down into the XY plane. In reality, it is actually precessing at the Larmor frequency within the XY plane. But what we've done is we've just supplied enough energy to affect a 90-degree rotation. So we call this a 90-degree flip. So it's a 90-degree pulse that we have applied to our sample in this particular instance. Now, because our vector M0, which we now call My because it's in the XY plane, it will actually induce a voltage in a neighbouring receiver coil. And this is basically how we measure our signal in MRI. Now, this principle is called Faraday induction. It works on the same principle as a dynamo on a bicycle. So you have a bicycle wheel here. As the wheel is turning, it rotates this device here. There's a small little bar magnet inside here, the North Pole and South Pole. So it's rotating around. And if we just have a simple loop of wire here, this rotating magnetic field will cause a change in magnetic flux through the coil, and it just induces a voltage in the coil. Now, our situation in the body is not dissimilar at all. We effectively have this vector M, which is effectively a magnetic field. It's rotating around in the XY plane at our Larmor frequency. And so if we put a small little loop of wire, a detector coil here, it'll induce a voltage in this detector coil. And as the vector is pointing towards the loop of wire, we will get a positive voltage. And as it is directed away from the loop of wire, we'll get a minimum in our voltage signal. And as it's precessing around, we would just expect to measure a sinusoidal voltage signal in our detector coil like this. And this obviously is a voltage signal which has the same frequency as our precessional frequency of our vector. So this is what we had before. My is precessing around in our XY plane. We would expect to see this, but in reality, the signal decays away. So remember, we have excited the system, which means M, which was initially along Z, is now precessing in the XY plane. The signal gradually decays away, and we talk about this free induction decay signal. And there are various relaxation processes, which we'll talk about in a moment, which contribute to this. But the net effect is the strength of this vector M gradually dissipates. Remember, M is the ensemble average of many trillions of hydrogen nuclei with their magnetic moments all pointing in the same direction. And what tends to happen is they tend to dephase, so they tend to spread out. And so as they're pointing in different directions, if you do a vector summation, the net effect is that M gets a bit smaller. So it follows a kind of an exponentially decreasing shape like this. And because if M gets smaller, the size of the voltage that we measure gets smaller as well. So M is effectively what our measured signal would look like. So it turns out we can derive an expression, it's a very simple equation, which describes the rate of decrease, the rate of decay of our signal, e to the minus time divided by T2. T2 is just a time constant, which describes the rate at which it's decreasing. It describes the rate of decrease of m, and hence the rate of decrease of the signal that we measure. And it turns out this value of T2 occurs due to the interaction on a molecular scale between the magnetic moments on neighbouring nuclei, so within neighbouring water molecules. So it's called spin-spin relaxation because it's related to the interaction of neighbouring nuclear spins. And because it's happening at such a molecular level, this T2 property is very, very sensitive to interactions and hence to the molecular environment that the water molecules happen to find themselves in. And it turns out that if you look at different types of tissues and even different pathologies within tissues, the value we can actually measure, people have done this, they've measured the value of T2, how long it takes for the vectors to decay away, and it varies widely between different tissues. And we can use this property to create contrast in images, so we can acquire images which are influenced or weighted by this T2 property, so-called T2 weighted images. So if you look at MY, you can see for the case of, say, fat molecules, the signal will decay very rapidly. It's got a short T2 value, whereas something like liquids, like cerebral spinal fluid, tend to have a much longer T2, so they'll decay much quicker, and soft tissues have many, many values in between. And we're talking like 10, 20, or 10, 100 milliseconds for this to occur. So that's a timescale over which our signal is actually decaying. There is a second relaxation mechanism that we need to be aware of in MRI. So we have actually excited the spin system by promoting spins from the lower to the upper energy level. They will eventually drop back down again, and so they will flip back to being parallel. There's a time constant called T1, which describes the time over which this occurs. And what happens is the energy that we've given to the spin system, as the spins flip back to being parallel, they give off energy, typically in the form of heat, so it's given to the lattice of the material. So it's called a spin lattice effect, spin lattice relaxation. And again, if we look at as the spins are dropping back down to the lower energy level, the value of our vector M0 is slowly recovering. So immediately after we have excited everything into the XY plane, the signal dissipates, but everything is still in the excited state at this point. Our signal has just decayed away due to T2. But what happens then is the spins drop down to the lower energy level, and as they're doing so, the vector M recovers back along the Z direction. So here we have a recovery, and it recovers again following a type of exponential curve, 1 minus e to the minus t divided by the time constant T1. And again, it's very, very sensitive to the molecular environment. Different tissues will have different T1 values, and this is the basis of another contrast mechanism called T1 weighting, which we can introduce into images. Okay, so I'll move on to talk very briefly about the main block components that you have in a modern scanner. So I showed you this picture earlier on. It's a clinical scanner you find in most hospitals. Typical magnetic field strengths are either 1.5 or 3 Tesla. 3 Tesla will be the maximum field strength that's currently permissible to use in a kind of diagnostic hospital environment on patients, although there are research systems which go to 4.7 and 7 Tesla and even higher again. And they come in different flavours. This is a system where there's a gap in the centre of the main magnet itself, so you can do some interventional work. This is another scanner. Magnetic field is horizontal. The person can actually stand. This has the magnetic field in a vertical direction, so you can get more access in if you want to do some intervention to the patient while you're imaging. And there's even scanners which are mobile, so you can find them in the back of a large truck like this. There are other systems which are called small bore for imaging small animals. They would typically have a bore size 20, 30 centimetres perhaps. Because they're that bit smaller, we can make the magnetic fields larger. So they typically start around 7 Tesla, 9.4, 11.7 Tesla are fairly common. And they would have a variety of different inserts for optimizing the imaging to get much higher spatial resolution, which you would need when imaging the small anatomy in small animals. Now, again, if we consider our sample like this, and it's all sitting in a very large static magnetic field, when we put our radar arrays in, the signal we get out is from the entire volume of the sample itself. And in NMR spectroscopy, what we're doing is we're detecting different metabolites, perhaps, or different chemical species within the volume. Each have a slightly different frequency, and we can separate out the frequency to produce a spectrum. Now, if we want to move on from a spectroscopy to an imaging experiment, we just add one extra component called magnetic field gradients. This is a third device within the scanner itself. And this was the invention, or the concept in the 1970s, which turned spectroscopy into an imaging technique. And so, in addition to our whole sample here, everything's sitting in a magnetic field, we put our energy in, but because when we're applying our energy, we have this additional magnetic field turned on, it's causing us to only excite spins or water molecules within a thin slice within the body. Okay, and then by using gradients in the two other orthogonal directions, we can separate the signal from different positions, and so we can produce an image. And so we have very small voxel volume elements, very small pixels, if you like, within here, and the signal we're getting is from all frequencies within that, if you like. So we're basically sacrificing any spectroscopic information in favour of imaging with higher spatial resolutions. So if we look at the very basic elements of a spectroscopy system, you just need a very large magnetic field, which has to be very, very uniform. You need something to transmit your RF energy into the sample, something to measure the signal coming back. And now if we add this additional component, these magnetic field gradients, we can now do imaging. Okay, and sometimes the transmitter and detector or receiver are joined together into one transceiver coil, although generally we do tend to separate these two functions. So this is again the scanner. If we take all the covers off, this would be what a standard magnet would look like. It just generates a very, very stable, very uniform magnetic field. B0 has to be very, very uniform over quite a large volume to fit a patient. Nestled within this, and this, you can see the cylinder here, are the three additional magnetic fields which we turn on and off very rapidly during an imaging experiment. So they create holes in noise, and they produce three orthogonal magnetic fields which vary in space in the x direction, the z direction, and the y direction. And this is what they look like here. And again, nestled within this again is the device which we use to transmit the radio waves into the body. This would be the radio frequency coil. This would be called a body coil because it surrounds the patient. And all of these are actually contained under the covers of a scanner like this. Now, to measure the signal, we generally make use of separate detector coils, as I mentioned. They're sometimes called surface coils because they're usually located near the surface of the body, also called receiver coils. The ultimate image quality that we hope to obtain is determined by the signal-to-noise ratio, so signal divided by noise. So what we want to do is we want to maximize the signal while minimizing the noise. And the noise comes from all the electronics in the scanner itself, even from the copper wire that the detector coils are made of. Then to maximise our signal-to-noise ratio, to maximise our signal, there's often not much we can do about the noise except for making our detectors as efficient as possible. But we also want to fill the coil. So what we want is if we're imaging a signal from the brain, we want our detector to be as close as possible to the brain. So you can, in this example here, this is effectively our surface detector coil, which is wrapping as close as possible around the brain. So the signal is coming, remember, from all the hydrogen nuclei within the sample. Okay, so we need our detector to be as close as possible. And so we tend to have a range of these detector coils depending on whether you're imaging the wrist or the shoulder or the eyes or whatever. So whatever the anatomy of interest is, you use the appropriate coil. Okay, I'll just finish off by talking about some of the basic image protocols. When we're acquiring an image, we run what we call imaging pulse sequences. Now, these things, you can see many diagrams looking at this. Effectively, they're timing diagrams. They describe when things are, when we apply things, when we turn them on and when we turn them off. And different things like when we put in RF energy. So we have enough energy to create a 90-degree rotation. And then at this time point, we have enough to create a 180-degree rotation. And we have many variations as well. We have timing diagrams for when these magnetic field gradients are turned on and off. So it's turned positive here, negative here, on, off, or sorry, positive, negative. And again, other gradients are turned on and off at different times as well. And by a combination of all of these, we can acquire signal, a bit of signal here, a bit more signal here. Okay, so this would all happen within milliseconds typically. And they can be fairly complicated as well, depending on what you want. And there's many variations of these. It turns out that this is what we had on the previous slide. We have to run this, and then we have to do it again and again and again and again. And the number of times we have to repeat this depends on the spatial resolution that we want. The higher resolution, the more times we typically have to repeat this, and this gives rise to very long acquisition times in MRI. Now, if we look at a very simple sequence, the first iteration, between the first and the second and the third, what tends to be varying is just one of the one property, this phase encoding gradient is called, and in this first instance here, it's got a maximum amplitude. It's decreased a bit smaller again, it goes negative, and it's more and more negative. And we typically just have to acquire this many times to acquire our image. Now, if we look at the signal, this is a signal we're actually measuring the first time around. It's an analog signal. We just digitally sample it. And what we do then is digitally sampled data, we just fill into a matrix in the computer. And this is what people call K-space. It's our raw data. So all of this data here just fills in the first line of K-space here. And then the second iteration, this signal is sampled, and it forms the next line here, and again for this one, and again for this one as well, until we've done this a number of times to fill all of the lines that we require. Now, this is just a matrix of numbers. People sometimes visualize it like this. It doesn't really mean much to our eye. We need to do a mathematical operation, a Fourier transform, to convert this into an image. And that's the basis. So again, the more of this we acquire, the better quality image will be. It turns out this all happens fairly rapidly, typically tens of milliseconds, and we tend to have to wait a long time, maybe even seconds, before we can do the second iteration, not to mention the third and fourth, and often there could be upwards of 200 iterations, which gives rise to our long acquisition times. And the reason why we have to wait such a long time is we have to wait for, we have excited the sample, we have to wait for it to recover back along the Z direction before we excite it again. And it takes quite a long time to recover along the Z direction. T1 times can be quite long, hundreds of milliseconds to some seconds at times. And so acquisition times of minutes are quite common, although it is possible to image very rapidly as well. And by varying the T1 property, this repetition between when we acquire the first bit of data to the second bit of data, we can introduce T1 weighted contrast. I'll just very briefly talk about, I mentioned when we put in our signal, or energy, our signal decays away like this. This is not quite the case. The signal tends to decay away much more rapidly according to what we call T2 star. And this gives us the possibility to introduce another type of contrast. The contributions to T2 are the T2 star is the actual T2 molecular process we talked about already, but also, say, non-uniformities in our main magnetic field. And it turns out that the signal decays very rapidly like this, but by applying an additional piece of energy, we can cause the signal to bounce back again, and we can form an echo, what we call an echo of our signal out here. And we can control when the echo occurs by varying this additional parameter, time to echo. And this gives us the ability to introduce T2 weighting into images. So that's the basis of that. And again, by just varying the echo time, we can produce very different appearance in our images. I mentioned this is our K-space, our matrix of numbers. We've actually acquired a lot of data here, so we get a high-resolution image. It takes about 4 minutes. If we only acquired half of the K-space data, so it takes place in half the acquisition time, the image quality is that bit less. So this just illustrates the need to spend, the longer you spend imaging, the better quality images you'll get. So just to finish off, a quick summary then. So MRI is based on the magnetic properties of nuclei, mainly hydrogen, although there's a lot of activity imaging sodium and other nuclei as well. The signal tends to be quite a lot less with these other nuclei. We have three main magnetic fields, our B0, which is very large and static, our B1, which is our RF energy that we excite the sample with, and our gradients, which enable us to spatially localize to produce imaging. So we talked about the different hardware components which generate each of these functions, and we just talked very briefly about the imaging protocols which determine timing diagrams when things are applied and turned on and off, and there are many different types producing different image contrasts. So I think I'm have my time there, so thank you very much for that.